and attend the class and pay attention. And I hope this, again, online class is more effective than in class. Okay, so chapter 8, shaft and torsion. In this chapter, first we will drive the torsion theory and deformation of a shaft, mainly with a shaft, a circular cross-section, and we will drive the relation between the shear stress caused by the torque which we apply. Okay, torsion theory. But before we cover this one, I again want to emphasize the general flow. This flow chart will equally apply to this torsion theory. Okay, here we will have a shaft. Okay, mainly the cross section is the circular cross section. I will draw in this way. Okay, this is a slender type, well, a long, slender shaft. Slender means that the dimension of cross sections, these lengths, will be much smaller than lengths, or the length is much longer than cross-sectional dimensions. And then this is a geometry, basically. And here we apply the torque. Okay, torque is one of the moment we apply. So we twist this shaft, and this will have a material properties. We will discuss more about the material property we need, but mainly shear modulus. That's the material property. And this is the torque, and this is the length, and this will be diameters. This is the given problem statement for this torsion theory. Now, as you can see here, what we are given is the force. Force in this case is the torque. That is this force. And now material is a shear modulus, and that is the material property we have to know in advance. And then the geometry, the deformation conditions is that we have a certain boundary condition, deformation condition. So actually, we have to apply the torque, or we have to fix here. That's actually the same. And this reaction force, this one can be caused from the equilibrium, but this is the deformation conditions. Okay, so this is the given, and basically we would like to drive the relations between the force we apply and deformation we will get. Get deformation, how much you rotate. We will have a certain rotational angle, and to get to this relation, T as a T will have a relation with the angle of twisting phi. To do so, first we need to consider the equilibrium condition, and also deformation condition, which is very important in this torsional theory. And of course, this stress-strain relation, this part is simply a sigma, or let's call tau in this case, tau, g, gamma. There is a reason why we call tau and gamma instead of a sigma xy and gamma epsilon xy. It's the same thing. Sigma xy equal g epsilon xy is the same thing. But this cross section is a circular. We will use a symbol tau for shear stress and gamma for shear strain. And stiffness is the same, G. So this is the material property which we will use in driving this torsional behavior. And what is the equilibrium conditions and what is the deformation condition? That's the main topic we need to study. And then finally, we will have this is a torque we apply, and this is a deformation. How much angle will twist? See, again, we fix it here, we apply the torque here, there will be certain rotation angle. This is the rotational angle, and that is the amount we want to drive. So the torque and phi, and there is a material properties, and so on. So these 3 plus 5 plus 1 flow chart is equally applied to this torsional theory. I just want, as I emphasized so many times, and again, I want to remind you of this fact, and please keep this in mind again. So whatever topic, subtopic we are studying in this chapter will belong to this category, equilibrium and stress-strain stiffness relations and deformation condition. And then we will combine them all and come to a final equations. Okay, so that is called torsion theory. Okay, first of all, we need to define what is the shaft. Definition of a shaft. Well, the shaft is again, the geometry-wise is the long, slender structures we call one-dimensional structure and longer than the cross-sectional dimension and subject to a torsion, twisting in this case. And there are many different types of a shaft. Okay, shaft. Shaft is the structure which will be subject to a torsion. Okay, that is the structure. Shaft is, we call this structure as a shaft. So depending on the cross sections, okay, depending on the cross sectional shape, we could have many different types of shafts. Not only geometry, but also the theory are different depending on the types of shafts, the cross sections. Okay, first one is the solid cross shaft. Solid cross shaft, solid circular shaft. Circular is this cross section is a really circular shape and uniform. Any cross section will be circular. And there is a solid versus hollow. Well, hollow circular shaft, well, as you can see here, the shape is a circular as a solid, but here we have a hollow. So this one, we have a big hole, and the theory-wise, this can be simpler. Hollow circular shaft, the theory-wise is a simpler than solid. And another cross sections we can think of is the non-circular shaft. Okay, these are all, say, circular cross sections. Whether there is a hole or a solid, they are all circular cross section. But other than circular, it can be called non-circular shaft. It could be rectangular, could be triangle, could be elliptic. Any other shapes other than circular can be called non-circular shaft. The theory-wise, it's much more complicated than circular cross-sections. And another one is the thin wall. Okay, thin wall. One type is the closed, the other one is the open. Okay, thin wall means that this thickness, okay, any thickness, this thickness can vary along these circumferential directions, but the thickness of this wall, it can be thinner than other dimensions. Okay, that is the thin wall. But the closed means that this circular, is closed, make a closed loop, and whereas this open one, there is the open slot. So it is open. So this is a closed, and this is the open. So depending on whether the shape is closed or open, the theory, torsional theory is quite different. In other words, the behavior of this shaft is very different from each other. Depending on the types, cross-section shape, and depending on the closed or open, all theories are quite different. And very important to know what kind of what types of shaft we can think of. But theory-wise, we would like to focus on this circular shaft, and we can cover the solid or hollow. That is the about types of a shaft, and this is the important to start with. Now again, so we will focus on the circular cross sections, and let's consider a deformation. Okay, deformation. You remember, we need to consider deformation conditions. In other words, we have a shaft. Okay, shaft I will draw in vertical directions. Okay, we have a clamp, and we have a rotation or deformation. That has nothing to do with the torque we applied yet. Okay, we don't consider torque, but we do have some deformation. Let's say deformation, this smart vertically, it rotates something. Okay, rotates something. And what kind of deformation we need to consider what this shaft will experience. That is about the deformation. And later we will consider equilibrium conditions, and then after that we will combine all of them. Then that is called, we will come up with a theory called torsional theory. So anyhow, we will consider deformation condition. Okay, so before deformation, after deformation, this is the A shaft, and say fixed at the bottom. Okay, fixed means let's make it bottom as the reference in terms of displacement, so it does not move, and then the top surface it rotates. Okay, well, rotation is mainly caused by torque, but again, we don't want to consider the force we apply. We just want to consider deformation, rotation. So this represents some kind of a rotation angle. Now, after this deformation, let's consider this A. Before deformation, there is A and B and C and D. This is just arbitrary mark. Okay, there's arbitrary mark, and And after deformation means that this A will move to another point we call A prime. So the AD now will make a line A prime and D. And now the most important point in this deformation field is that what will happen to this line from A to B. That is the one of the main point. And as you can see here, since B and C are fixed, the line connecting A and B, now the line connecting A prime and B will be straight. Okay, this will be the straight. If I draw here, that will be a straight line. Why straight line? Well, there is many reasons for that. In terms of geometry comparability, there are many reasons for that, but this is a fact, and this one has to deform. I mean, the straight line. Okay, so this is a deformation before deformation, and this is after deformation, and consider this arbitrarily plane, arbitrarily line, and this is and consider what will happen to them. Okay, this is the very best, very first a deformation observation. Okay, this you need to visualize whenever we apply the torque to the shaft. This is the deformation the shaft will experience. Okay, it's very important to visualize that. Now, this visualization or this deformation needs to be expressed in terms of equations. Okay, well, we certainly can draw this line, but we need to convert this geometric deformation into equations. So what kind of equation we can think of? Here is the equations. First, let me draw it here again. And this line, and come to this way. Okay. Now, any point here, or even inside. Okay, this is just a appearance on the surface. But imagine inside. Imagine inside, a little inside. Okay, I will draw this line, and this line comes to this point, right? And any point, not only on the surface, but also inside, we need to think of some deformation. And this is a cross section and this plane, not just on the top, but also inside the structures. Okay. So here is the point, arbitrary point, which we need to consider for deformations observations. And so this one, say this one is the R coordinate, and this one say phi coordinate. See, rectangular Cartesian coordinate, which makes perpendicular to each other, is x, y, z, but also r theta z is also a Cartesian coordinate, means that this r and this is a phi, and this one is the z. Okay, z is along this axis. So r phi z is the very important coordinate. And notice that each line we have another r and another phi. So r and phi, the coordinate is changing depending on the positions. Okay, so we can have displacement in phi direction, u phi, and this displacement and ur. We are focusing on this point, and it could have a displacement r, ur, and displacement phi, u phi. I'm sorry, not phi, theta. Okay, u theta, and sorry, it's not the phi. This is a theta coordinate wise, and this is the angle rotate, so that is called phi. Okay, so U theta is simply proportional to R. R, in other words, that here the point is this is a U theta, and this is a U theta, and that is a U theta and U theta. As you can see that this U theta is a R times phi. Phi is the rotational angle. So U theta is simply R times phi. And importantly, this circular cross-section shape does not expand like that, does not shrink, which means that UR equals 0. So always there is the displacement field in hook direction, theta directions, and that is the proportional to R, and this is the angle of rotation. Okay, angle of rotation. Now this angle of rotation phi, okay, phi, let's say we establish the coordinate. Here is the z, and z position-wise here, here. And now at any point at z, here is the at z, okay, arbitrary positions. And this angle of phi, let's say this is the phi, okay, this is the phi, angle of rotation, this is a phi. Phi is the a phi is a function of z, right? Simply at the bottom, z equals 0, the phi equals 0, right? And z equals L at the top, say this one is the L, then the angle twisting will be phi 0. I would call phi 0, which is the occur at the top surface. This will be phi 0. Again, pay attention, please. This phi is gradually increasing, as you can see here. If I draw, this angle is gradually increasing, and from 0 to phi 0. So we can say that phi is a function of z, is proportional to coordinate z. What is a c? Well, c is the proportional constant, which is not known yet. This is unknown c. And phi, but what we know is that phi is simply linearly proportional to z. So phi can be set c times z. And then we put it here, then simply U theta is a proportional to R. R is here, and z is here. So there is a proportional constant c and R times z. And again, R equals 0, no radial expansion, and also I need to say z direction is no extension. So uz equals 0. Uz equals 0, what does it mean? It means that when you rotate, the length L is the constant, kept constant, and this UR0, what does it mean? This radial dimension does not change. It is kept constant. Only deformation we can observe is the hook directional U theta, which is proportional to R, proportional to the Z. There is a proportional constant. Okay, that is the geometric displacement, and that is the what we observed. So this observation can be written as an equation that UR equals 0, UZ equals 0, and most important term, U theta equal some proportional constant C times R times Z. Okay, so this is a geometrical description, and these are mathematical expression. So that is the same thing. So when you apply torque to a shaft, and this is the deformation we have. And again, this equation, get back to this flow chart, and deformation is that we can say that we have U theta will be C times R times and Z, and others like U R and U Z equals 0. That is the deformation condition. That is the deformation field the shaft will experience. In a sense, it looks relatively simple, but this is the most important observation, okay, deformation observation in torsional theory. This kind of deformational observation is a very important step for structural analysis. Later, we will cover another structure, it's called beam, okay? Another structure we will cover will be some kind of beam like that on the vertical load, and this will deform. And in derivation of a beam theory, the step will be very similar. We first observe the deformation field or deformation condition, and then consider equilibrium and stiffness, and we all combine together. Torsional theory is exactly the same procedure. We observe the deformation and equilibrium. We will consider equilibrium and stiffness, and we come up with a torsional theory. Okay, so again, I cannot emphasize enough how important this flow chart is. Okay, and now once we have the displacement field, I will rewrite here. U theta will be C times R times Z. Now, UR equals 0, UZ equals 0. Now, once we have a displacement field, what is the next step? Next step is simply strain definition. Remember that epsilon ij equal ui xj and plus uj and xi. This is the differential expression, but simply in a simple way, epsilon xx will be, xx then ux and uy, and epsilon xy will be a half of ux, uy, and uy and ux. So we have 3 terms of a normal strain and 3 terms of the shear strain, and so as you can see, all the strain is in terms of displacement. In terms of displacement. So since we have this strain displacement field, next step is simply to define a strain field. Okay. Strain, here, what we, from our observation, this will move to here, right? And that line will do the same thing here. So this one goes like that. So pay attention to this kind of, the pi type, piece of pi, this one will be A, B, F, and G, and this is O. And now you can see that this moves like that, right? Moves like that. Now, what kind of a strain field we would have? Very simply, as you can see that there is an angle change, right? There is an angle change from this rectangular to this shape. So this is exactly what we observed in defining the shear strain. So in this case, the shear strain is this a gamma. This is gamma, and Z and theta. Well, YZ and YZ. This is a Z, and this is a theta. So this is a Z, and this is a theta. Well, you can say this is a theta, and this is a Z. So this is a epsilon Z theta or gamma Z theta. And this one, how do we define? Well, again, epsilon Z theta, by definition of this shear term, very similarly, you can say that epsilon theta divided by Z plus epsilon Z divided by theta, and in theta, dimension-wise, you need a R here, and you need a half here. So once we observed this displacement U theta and function of Z and UZ, we don't have it, but U theta, this one comes to here, and what we have half CR, right? That's the strain field. That is a strain field, but this is the, in terms of engineering strain, that is the gamma. Actually, the gamma, when we define, this is twice of this epsilon. So the gamma Z theta will be simply C times R. Okay, C times R. So this one, then what is the C? What is the C? That C is the very important a value, and this C we need to observe one very important point is that please consider this one is this coordinate is the R. Okay. R times, this is the rotation phi equal, I would consider this one is the dz. Dz means a very small part of this shaft. And so R times, R is here, R times, so this angle will be d phi. R times d phi will be, R times d phi is the what? I will draw, I will use a different color. You know, it will indicate this length, right? R times, this is the R, and times d phi will be a this is a height, is a dz times, what is this? This one is the as we define gamma. Okay, this is the shear strain gamma Z theta. So gamma Z theta times dz. That is the length of this green line. Okay, this green line can be calculated from here. This circle, and can be calculated from this way. So from this identity, we can have gamma Z theta. So gamma Z theta is simply R times d phi dz. Okay. Well, this is we need to remember this derivation, geometric observation. So anyhow, that's why we got this one, and consider these mathematical expressions, gamma Z theta. Now the C is the same as the C, which is now constant. So this constant, we can see that it's nothing but dphi dz. Okay, dphi dz. So constant z is the rotational angle per unit length. Okay, dphi dz means that, in other words, can be said as the angle per unit length. So which is the constant. So you can say that this is the, when we apply the torque, constant torque through the in each cross section, this can be said, and total phi divided by L. Okay, d phi dz can be called phi 0 divided by L. Well, in general, we can say d phi dz. Okay, so again, I have this one, this A prime, A and A prime, which is this one, but that is the d phi, and this is the R. Okay, R times d phi is this one, R times d phi, and gamma z theta times is not shown here, but this height is a dz. So that's why we have a dz here. So this equation easy to forget, but the most important a geometric deformation condition which we need to use to come up with this dphi dz is a constant. Okay, that is a story about a gamma z theta. So I will write down here again. The point here is that this is a displacement field. Now the strain, as we just drive, the gamma z theta is the, again, we magnify this part, and this will have a certain shear deformation. You know, the shear is changing the angle, and that is the what? dphi dz, which is constant, times R. So this is the A constant, and you can see that gamma shear strain is the proportional to R. You can imagine that y is proportional to R. This is a center line here. That center line here is, you can think of the surface, and as you can see that each rectangular will deform like that, and this one will deform like that. And so this deformation, the gamma, this angle is proportional to R, and this is the constant. Okay, so I'm repeating the same equation and same procedure. This is a displacement we observed from the shaft deformation, and this is the strain field we can drive from this displacement field. And so this is a strain. Now, as you can imagine, we need to consider equilibrium conditions. How much stress will now I will draw and cross sections, any cross sections inside here, and this is subject to a torque. That is the external torque, and now this torque will generate a certain shear stress, which will be sigma. This is a z, and theta. Simply we will call that as a tau, and there will be a tau stress generated by this torque. That is the equilibrium conditions. So that is the subject we will drive. Okay, so here it is. And again, as I mentioned, the torque is the applied load, and shear stress in red here is this. Every section we have a shear stress. You know, all the over the all cross section and all over the all R directions, we have a shear stress like that. And now, whatever shear stress we will call tau, and tau is a function of what? Theta and function of R. But in theta wise, that is pretty much axisymmetric. We can easily imagine that. And so it's not a function of theta, it can be simply a function of R. Now, so by definition of equilibrium, whatever we apply, T will be, this is the external load, and this is the internal load carried by tau. Tau is now here, let's consider a cross sections, and tau is applied here. So tau times dA will be the force over this cross section dA, and there will be R. Okay, R is now Torq, and integration will give us the Torq. Okay, so again, I will rewrite tau times dA is the force, and then we need to multiply R to come up with the Torq and integration over the area. That's the external torque of T. Okay, now this is the basically equilibrium equation. External load, and this is the internal stress distributions, and they need to be equilibrated. And then, importantly, this is the tau. What is the tau? Well, tau, we have a stiffness, tau equal G gamma. See, there's a tau there, and you remember there is a gamma which we already have. So tau will go in there. This is the equilibrium. Okay, equilibrium. Now this is the what? Stiffness matrix, stiffness relation. And what is the gamma? The gamma we already have, dphi, dz, and r. So this gamma will go in there, this tau will go in there, and then let's see what the final equation will be. So the tau is simply G gamma, this one again the stiffness. So obviously this stiffness, tau G gamma is the one, tau equal G gamma. I can write down here. So the equilibrium equation T Torq will be, remember the tau dA is the force, and you need to multiply R. That is the equilibrium. So this tau will be here, and then G will be the stiffness. Where is the gamma? Gamma we already have. So gamma go here, and tau go here, and this is a torque we externally apply. So let's do simple integrations combining all these equations. And here it is, and tau, and this one gamma. Gamma is this part, and put it here. Okay, so remember there's R there. So the tau comes here, and G gamma and things. So G is here, and there was R here, and there is R here. So we have a twice of R, and dphi dz, and integration of A will be total T. So what is the dphi dz? Dphi dz is a constant C. So the constant means integration out of integrations. And what is this one? R square dA we call polar moment of inertia. We can call IP. So simply this is IP and T and G IP. Okay, this one is the final equation we come up with. Okay, so T dphi dz and GI. Okay, this is the final equation combining. Say this is the torque we apply, and this is the deformation we observe. Okay, that's the overview of the torsion theory. And I hope it's very clear that the torsional theory just follow all the 3+5 flow chart. Okay, Okay, so this is all I want to cover today. And again, we will upload this video and see you tomorrow. Okay, thank you. 다 녹화?
네, 다 녹화되고요.
이거 조시 빨리 또 해야 되잖아.
네, 초대해놨습니다.
오케이.
네.
진행 좀 해줘.
네, 알겠습니다.
새로 세션 새로 열어야 되잖아.
예.
끝내고 나한테 잠깐만.
네.